speak Dominic, coming from Berlin, who's going to talk about the moduli of double covers.
Thank you for the invitation. So yeah, today it's quite. I mean, it's nice to talk the day after Francis's course kind of came to a close, because we'll essentially do some very explicit non-reductive GIT, right? So this is kind of the advantage and nice things about this. What I'm going to talk about. It's really you really get proper hands-on experience with non-reductive GIT quotients, and you get to study moduli of, well, in a sense, moduli varieties, but we'll see a certain piece of the moduli stack of variety. We'll see why. Yeah, I mean, the moduli varieties picture is a lot more complicated than the moduli of hypersurfaces picture and what you lose going in between. Okay, so I tend to start talks about these things with the motivation given by this kind of very old classical problem. There's this moduli of hypersurfaces, degree D inside Pn. Okay, this is a well-known story. You take Y, which Y will be abbreviated for Y and D, and this will be the linear system, okay, of degree D hypersurfaces. And this admits an action of PGLN, which we normally replace with SLN, which is kind of almost up to finite groups. Isogeny, stereomorphism, EN. Okay. This is a kind of very old and well-studied problem. We'll define notation which we'll kind of use throughout the talk, which is M. This is for MD, which we'll define as the quotient stack of Y by G. Okay. And as is kind of relatively, as one can imagine, before imposing any stability conditions, this is very badly behaved. This is badly. So in particular, in this form, we have a unique closed point. And even some of the kind of naive things that one would do in order to rescue this end up not, you need some relative, well, you need the sophisticated machinery of GIT, right? So we'll define a substack inside here as some star, and these will be all hypersurfaces in Pn with property star. Okay. So for example, my favorite example of this to see why we need something a little bit more sophisticated is you just require that all hypersurfaces in all your families be normal, okay? Then the only closed points are of this form. So you can create some limiting, you can always create a limiting family of normal hypersurfaces, which bring you to essentially, three very reduced things. Okay, things like this. So essentially, you reduce it down to plane curves. I mean close point. I mean C points. I'm also always working over C. Sorry. You mean is it? I mean, I suppose here I take the C points of the coarse moduli space. No. I mean, there is no coarse moduli space in this point. Sorry, so I think I do mean the complex, or the closed. I think I mean the closed point. Thank you. Right. However, GIT comes to save us. Okay, so reductive GIT applied to this SLN action gives us a notion of stability. Okay, so fine, so Y S to be semi-stable hypersurfaces inside Y. Okay, I won't define what this means, But we have the following picture. So we have like this. So we have M smooth, okay, openly contained inside M stable, openly contained inside M semi-stable, and this should be we have Y minus a discriminant locus. Modulo G openly sat inside Y S modulo out by G openly sat inside Y. So G. And here we have a course, this being a course moduli space, and this being a force moduli space, this being a good moduli space. Okay. Right, and so this is kind of along with the properties which I'll go on to list about this particular modular problem. This is what we're going to be aiming for, right? So what properties do we know? So these two are both. What are they? They are quasi-projective, and they have finite quotient singularities. Okay, all of them are normal. At least a little bit of geometry. This one is, of course, projective. And there's one at the end here. This is actually a fine union. So got some geometry about this. So this is the picture that we kind of want. So properties and issues. So the first is that we, in this case, so again, I suppose let's take the notation I want to give these moduli spaces names, the course moduli spaces names. G, or the moduli spaces name. Is it confusing? Yeah. We understand the C points of S, okay. And these correspond to isomorphism classes. Of variety. Okay. So this here we need a restriction on the if this holds if firstly n we're not considering points, and we have two bad cases which are plane cubics and quartic surfaces. Actually, why, I mean, this one's less interesting, but why this one fails ends up with some kind of nice geometry. The upshot is that, for hypersurfaces outside this case, their isomorphism type is completely determined by their linear isomorphism type, right? So, thank you. So, and yeah, the construction is very nice and geometric, how you come up with isomorphic K3s, which are not projectively isomorphic. And the geometry ends up, you can find quartic K3s, which are isomorphic abstractly as varieties. One contains 56 lines and the other contains 48 lines. That's a kind of nice, relatively recent work of Matthias Schutt in Hanover and some other collaborators. But the geometry is nice. So this is a result which goes back to Matsumura and Monsky. in the 60s. So this is kind of well known. We also know that generic stabilizers are finite, trivial, sorry, which means the coarse moduli spaces are honestly smooth, almost everywhere. So the next. Okay, we also know what M smooth looks like locally. So locally, this looks like an analytic quotient set. Okay, so locally looks like this at X smooth point. Okay. We have a nice local description, so we can cover this DM stack here with like analytically locally with stacks which look like this. Okay. So the deformation theory of smooth hypersurfaces is very well understood. And again, here I need to be making minor, so I need to be considering at least surfaces. It's not true for curves. Third is geometry and topology, so we can explicitly study these things. This is accessible. And we'll return to this later. So now the issues. So it is hard to compute stability, except in low cases. Low D and N. Okay. And what's the other one? And it's not really the right. It's not really the right stack. It's not really right. Moduli of varieties. But remedying this last problem is kind of very hard, sophisticated work, and this is this kind of program of families of higher dimensional varieties, which Kolar and his school have been working on for a while. Like, for example, so what I mean by this is that I can take a family, right, over some DVR, where the special fiber, well, let me do it the other way around. So the general fiber is a smooth hypersurface of degree D. There's a smooth hypersurface of degree D. And over the special fiber, this is a smooth non-hypersurface. Which means I can kind of leave my stack whilst performing degenerations which I would want to leave me in my stack, right? So the examples of these are actually really nice. And if I had a longer talk, I would write them down. The nicest one is kind of an example taken from Mori's master's thesis, but it very much relies on. So this relies on. Raise it up. Okay. This counterexample and the family of counterexamples which exist. This counterexample needs B to be composite. B times F. Okay. Okay. So there's kind of an open question, which is if the degree is prime, then this is not possible. And this has been confirmed by Autumn and Wagner. 2019, I think this was, shows that if B is equal to 5, then this is not possible. So smooth degenerations of hypersurfaces, of quintic hypersurfaces must remain quintic hypersurfaces. Okay. So it's something which does not admit an embedding into a projective space as a hypersurface.
But those are like families, the family that all of the fibers embed.
Yes.
Like,
yeah. So all of the fibers embed, if you like, this K lives inside here. Okay, as a hypersurface. Equivalently, I mean, whatever, take a true family over a disk or whatever, and every single fiber embeds into a hypersurface. But yeah, so as I've written it here, it has a consistent embedding, right? Which is even worse. I mean, right? So I mean, which is an even nicer situation. Right? So yeah, with a consistent embedding. So this is not possible. D equals 5 or ND equals 7. So we can't do it for septic surfaces as well, but their method doesn't generalize to septic hypersurfaces in general. Okay. Right. It's not embedded. Yeah, and it's not embeddable as in this case, it's not embeddable as a hypersurface in any case. I don't necessarily know. I mean, I suppose you would want it to. That is the case for this degenerate fiber. Yeah, so that's the answer to your question. I mean, I suppose it's a good. What do you want to break, right? Like, what am I looking for in this break? Do I want it not embeddable as any hypersurface, or do I want it not embeddable as an extension of this embedding? I imagine it's this one, but this one actually we have both. Okay, so yeah, let's move on to kind of new things. More time than I planned. Yes. So we consider xk times r Cartier hypersurface inside P11R. Okay. And we're gonna basically try and play this whole game and see how much we can recover and see what we can say about geometry and topology in cases which look like this, okay? Which contain so yeah. Here, this is K multiplied by R. So this is the degree. Okay. Right, and if K is equal to 2, then we end up with double covers of X inside Pn minus 1, okay, which was promised to you in the title. But I don't know a nice name for this more generalized notion here. For curves and surfaces, it's curves in a Hirzebruch surface, but I mean, it's equivalent to curves in a Hirzebruch surface. Right. So no, so when K is equal to 2, okay, a generic, a general F inside Y, which is going to be objectualization now of P-O-K-R, okay? For a general thing here, I can write this as, all right, let's put the coordinates on here will be X, and here will be Y, okay? So a general element can be written as F squared plus some F K R. Okay. So a general element F up to a change of coordinates, we'll kind of explore that a bit later, can be written in this form here, and like this, then one sees it. If you take the projection onto these first coordinates, then you understand this a general hypersurface here as a double cover along a degree KR hypersurface in Pn-1. So the picture being, I have my XKR here inside P. Yes, exactly. So, yeah. No. That's because I've written it badly. Pn-1 branched over. Thank you. Yeah, sorry. Yeah, good. Excellent. So this is what we're dealing with. So I'm going much slower than I planned. Let's go for, okay, so now the automorphism group of Pn, of this P1111R is equal to a general linear group acting on the x's. We have some scaling factor acting on the y, okay? And we have some unipotent radical, right? All of this needs to be modeled out by the GM, which this is the structure GM, which you construct using this, you use to construct this weighted projective space. Okay, so what's going on here? So I'll write U as, so U is basically n-1 OR here, and I'll write an element U as corresponding to a polynomial FU, next one to xn. What did I write?
You couldn't decide.
Yeah, it's because I wrote this afterwards, sorry. So this goes here, and now the grammar, which is, I agree, is not clear. If k equals 2, then we're considering double covers of P. Double covers branched over here. Down here. Yeah. So in this case, this is 2. And here, yeah. Yeah, sorry. I forgot that I was doing the specific case in this. Here. Yeah. But I mean, from this point onwards, I'm going back to general K. Okay. Right, so the automorphism group looks like this. An element in here, A, T, U. What does this do? Well, as this kind of, we understand this is an automorphism group on here. This sends the x coordinates to A multiplied by x, and it sends y to P, y plus FU. Like this. Okay. This is how we construct this group. Right. But to make our life easier, we replace this with G. It's going to be SLN plus GM. It's going to be direct product U, which as an isogeny maps onto P. Okay. This is a surjective map with finite kernel. Right. And so the GIT, at least of the course moduli spaces, is not going to care about replacing this action with this action. So then we let G act on Y, okay? And Y really is equal to this. So this is the linear system, right? And we want to play the same game. So we define M again. So M. When I need to be specific, as I will later, I kind of write this in this long form here. This is this quotient stat Y mod G. Well, yeah, I do mean it. Right. So now to do the same, we need to use this non-reductive GIT, we need three things. First thing we need is a graded unipotent radical. Okay. So I'm going to go through what each of these mean as I prove it for this specific case. Okay. So we need U stabilizers. We need trivial U stabilizers. Okay. And we need a well-adapted linearization. For the action on Y, okay? So we're going to go through and we're going to check that we have each of these in each case, okay? So first kind of result is that the following one parameter subgroup grades U, okay? Which means, so lambda G of GM acting on the Lie algebra of U has strictly positive weights. Okay, and I don't have enough space anymore to write down what lambda G is. Let's do that. This is via, so this action is via conjugation. And lambda G sends T to kind of take the standard minus n plus 1 in SLN and T to the n here, okay? Back inside our group here, and n just has to be strictly greater than R, okay? And in practice, later on, we'll take it much greater than R, but it doesn't really matter, okay? So the claim is that if one kind of goes through, this, so you take that U in the unipotent radical, act like this, so it sends Y to Y plus FU, some polynomial here, okay? Capital R is some positive number. Yeah, but what is this R? This is little r. Okay. So, yeah. So, I mean, this is essentially a computation. Like, so you just do lambda G of T dot U lambda T inverse, and you let this, you kind of just do the computation and see what this does to X, and see what this does to Y. And for time reasons, actually, I'll kind of leave this out. Okay. This is just a kind of a computation out of which this condition here, I mean, so the actual condition is just greater. So this condition kind of falls out of this computation. So, and then a remark. So for a general toric orbifold, so there exists a grading one parameter subgroup, okay? So let's give it a name, let's call it P, okay? In what P? This kind of I prove it in my paper on this on this topic, and a paper of Greg Beck, Brent Duran, Francis Kerr, and Thomas Hall. So what this means is that at least the first step of the kind of non-reductive GIT program we can run on all toric varieties with at worst orbifold singularities. The rest of it gets slightly more complicated. Okay. Good. So the next step in the kind of non-reductive GIT is to compute the weight spaces, the lambda G weight spaces for what I mean by this is just we let this act on Y. And at this point, we just take the kind of canonical linearization. Remember, Y is just some projective space. We compute the lambda G weight spaces in this case. And this is, again, this is very easy. So we take lambda G of T. We let it act on some, well, let's give us a form of F first. So we take a general F inside Y, okay? So it has the form, we have some coefficient of Y. So Y has weight R, so we raise it to the power of K. And we have Y to the K minus 1 times F. This will have to be R in the X's, okay? Plus all the way up to F, K, R. Okay. Now we take lambda G of T. We let it act on F. Okay. So when we bring this inside for the coefficients here, we basically flip the sign. So what we end up with is T to the minus K N. Okay. CF, its coefficient, times Y to the K. Plus, and here we have T to the minus K, well, minus N times K minus 1, Y to the K minus 1, FR, plus, and here we have to bring lambda G inside, so T inverse X1 up to Tn minus 1 Xn, and then KR. Same thing. Okay, I mean, again, let's not go through the full computation, but if you think about this for a second, you see that given how we've chosen our n, this is by far going to be the lowest weight, okay? So, this is by far the lowest weight. And it appears only once. So thus, the minimal weight space, okay, the projectivization of which we'll call Z min, is equal to a single point, this Y to the K. Okay. And the point is, I'll mention a bit more of this at the end. Non-reductive GIT quotients with Z min equal to a point are very, very simple and very, very nice. And you can really get a handle on what you're doing, which let you, in this case, have a much stronger handle on the actual moduli spaces you end up constructing. And this is very nice. So even though I know this seems like a lot of kind of computation, just kind of slogging through, but at the end you get real geometry out. This makes it worthwhile. Okay, so Z min is a point, right? And we define Y naught min to be all those F such that the limit when we flow down lambda G C on F is equal to Y to the D. Okay. And this is equal to all those F such that CF is non-zero. Okay. So we already see kind of these are the basic objects with which the unipotent stability are defined. Okay. And they're spitting out already very reasonable things. The Z min is a very natural kind of isolated, very degenerate hypersurface. And this Y naught min, which is going to make up most of the Y naught min, which is going to make up most of the U stable locus, it's just asking us for this coefficient to be 0. And if you want to calculate, and essentially this just corresponds to us having to avoid the unique singular point. So this is not in vanishing locus of F. If and only if the same point is not in the vanishing locus of the singular locus, and I mean the non-quasi-smooth locus. Again, we'll come on to that. This happens if and only if the coefficient of F is 0. Okay. So again, what this is telling us is that right at the beginning, we're throwing away hypersurfaces which are going to hit the isolated singularity. Okay. Good. Right. So then, so one can also kind of tell very quickly that if that the stabilizer and the unipotent groups of this point, Y to the D, are just trivial. Okay. If I take any U, remember, which takes Y and adds on a polynomial, okay, then if I need to ensure that I stabilize this, then I have to be adding on the 0 polynomial. Okay, this is really direct, and this is another very important part of non-reductive GIT. So this is B. And now this kind of well-adapted linearization. But again, the groups we're dealing with are very, very explicit. Yes. So I'll write that down explicitly what it is. But essentially, it's all very, very reduced hypersurfaces, right? So I can write it down here. So the U sweep of Z min, this is equal to all hypersurfaces of the form Y plus some R form, all to the power of K. Okay, looks like that. Just some strange twisted Veronesian inside this outline space. But yeah, so again, I'll write this down in the next result. What we're going to throw away for the U-hat theorem is just very, very bad hypersurfaces and hypersurfaces which contain this stacky point. Okay, so well-adapted linearization. So characters are very, very simple in this case, right? So we'll define so SLN has no characters, right? So what this allows us to do, we take matrix, we take some T, we send this to T to the Q, okay? And we'll take rational characters, okay? Now, in order to move on to kind of slightly more meaty stuff, I will kind of skip over this next bit where we prove very explicitly that this well-adapted linear that there exists a well-adapted linearization. But the point is, if I take Q now to be equal to minus Kn, okay? No, Kn, sorry, minus epsilon for some very small rational epsilon, then the linearization L, which we'll take O1. So again, because of the groups we're dealing with, to choose a linearization for this action is really to choose a bundle and to choose a character with which you twist. The linearization here is well adapted. And I'll draw a picture of what this means, of like how we know this is true. So, e.g., let's take x4 and p112. Okay. So what the torus weight. So this picture is going to be approximate, but it's going to be roughly true if we now take this n, with which the n that's inside this lambda. So lambda g went to this kind of, to this matrix and t to the n. So now at this point, just to draw the picture, for the mathematics, it doesn't really matter. If we take this n at this point to be much, much bigger, then the picture becomes approximately true. So what does this look like? So the torus weight picture breaks down to just looking at the monomials in the linear system. Okay, so we have x1 to the 4, we have x2 to the 4, we have all of the ones in between. Okay, then we have another group here where we have y, x squared, y, x1 squared. And at the bottom, we have y squared. Okay. So this is what our torus weight picture looks like. Okay, and the origin is sat just around here. So the origin in the torus weight picture. So this line essentially is going to correspond to the lambda g weights. So this kind of, the set of monomials is living in the torus weight. So for the entire maximal torus, within this lies the weight picture for this special one parameter subgroup we have, so the weights essentially of any monomial here, the lambda g weight of any monomial here projects onto this line to give you its lambda g weight, right? Sorry, so the torus weight of any monomial projects onto here to give that monomial's lambda g weight. And so this one down here is sat precisely at minus kn, okay? Because this was the weight at which lambda g acted on. So k is now 2 again, sorry. So, okay. And now you see if I twist by this action, all I'm doing is I'm taking the origin and moving it epsilon away, okay, from this thing here, okay? So then my new weight picture looks like, so the shifted weight picture, I just take the polytope essentially and just shift the origin very, very close to, so epsilon close to this guy here, okay? Now that's going to be very important, and that it is so explicit is going to be very important in computing and figuring out what semi-stability is, okay? Right. So let's have I might skip so let's have a quick definition and a result. So to get to some kind of specific examples, I'll give a condensed version. So we say that f inside y is semi-stable with respect to g. Is g semi-stable? So this is the definition which falls out the non-reductive GIT. If and only if f is torus stable and the torus here, G. Okay. So this is the kind of standard. So this is actually the Hilbert-Mumford criteria. We can out of the box use for quotients that are this simple. And then the next definition is that we say, so F is quasi-smooth. Again, in this case, quasi-smooth is equivalent to smooth, but the examples coming, it won't be. So F is quasi-smooth if and only if kind of Jacobi criteria is satisfied. Is not all zero. So there exists an I such that this is not all zero. Okay. We just have a standard Jacobi criteria for F. Okay. Quasi-smooth if and only if there exists no I for every x, y not equal to 0, there exists a non-vanishing partial. Okay. Okay. So now the kind of structure theorem for this is the following. So this is this is part of this definition, yeah. So if you like, the vanishing locus of F inside the wedge projective space is smooth as a substat. Quasi-smooth is just, yeah, it's a kind of natural, because we're dealing with hypersurfaces inside an ambiently singular space, right? An orbifold, so it has very kind of prescribed, in this case, cyclic quotient singularities. And we want to allow the hypersurface to inherit these singularities and still consider them reasonable, basically. And I mean, also algebraically, it's a very natural condition. I mean, just for straight projective space, smooth as if and only if all the partials don't vanish, right? And the same thing. You just write down the same thing. Right, so the theorem is as follows. So with the linearization as before, for G acting on Y, okay. Specifically, this is O1, twisted by OQ, right? Then we have the following picture. We have the quasi-smooth locus is contained inside the stable locus, contained inside the semi-stable locus. Okay. And again, we have, I won't have time to mention this at all, but we can, again, write this follows. So we can remove a discriminant hypersurface. And here we have, so this is coarse, and this is quotient. In this case, now we're just talking about quotients. So, geometric. Okay. So that's the first one. And then the second kind of point, which falls out of an inspection of the weight picture as well, is that, so for a given x inside this P1R, okay, and we say that, so suppose that x is of degree 2R, okay, so that it is a double covering of some hypersurface inside Pn-1, okay, then one has that x, or I've been using, f. So this name, then f is semi-stable, respectively stable for to this G group, if and only if this hypersurface here, the hypersurface, just the straight hypersurface in Pn-1, is stable for, yeah, I have to write the full thing. So 2R in Pn-1 is semi-stable for the SLN action which we have, okay? So that the non-reductive, so what that means is that the non-reductive GIT of F, okay, is exactly the reductive GIT of the hypersurface along which it is branched, okay? And again, this falls out of looking at the weight picture. Okay. So I will say now some applications basically of this. So the applications. So we'll start with Del Pezzo surfaces of low degree. Okay, so degree 2 Del Pezzo surfaces, or smooth ones, mean that they look like surfaces inside P1, 1, 1, 2. Okay. And what this means is that, so this was kind of done by hand. But Odaka, Spotty, and Son, I think in 2016, when looking at the K-stability of these Del Pezzo surfaces, they essentially still constructed the moduli space of K-stable Del Pezzo surfaces of degree 2, okay? And they showed that this is exactly the blow up along a special point, which turns out to be the blow up of what? So the blow up of curves, so quartic curves, the semi-stable locus. Quartic curves in P2, okay? You have to blow up at the double conic, so which is GIT semi-stable, strictly. However, when you take its branch covering, it doesn't give you anything. It doesn't give you anything reasonable. I mean, it doesn't give you anything. It's non-normal, and this is, yeah. This doesn't work. This doesn't work for K-stability. But you don't have to fully resolve the strictly semi-stable locus. You just have to resolve this one point, and it gives you actually the K-stable moduli. I mean, the K-polystable. Really. And here, I mean, I suppose as coarse moduli spaces, not as moduli stacks. Okay, but what this shows us is that, so one kind of quick remark, and we brush over this quickly because this means this is really nothing new. This is blow up along the same point of MSS of S4. So P1, 1, 1, 2. Okay. So the degree 1 case, which actually does lead you to something relatively new. So these all present themselves as sextic surfaces in P1, 1, 2, 3. And now this is not exactly the same as the kind of content that we've gone through, but if you do it explicitly, one finds that this is, in the same way, you get this as a double cover of P1, 1, 2 branched along a sextic curve, okay, on the singular conic. On this this quadric cone here. And what this means is that the GIT stable locus, so the stable locus for these curves, okay, is contained inside the K moduli for degree 1, okay? And again, this inclusion is non-trivial, and it's done in the same paper of Adaptive Spot and Sun, okay? So, but unfortunately, it's not quite as simple of a case of this. You can't get from this one to this one by including the semi-stable loci and blowing up, as far as I'm aware. Like the picture is a little bit more complicated, but you can. So the complement here, okay, the complement of this space inside here is again stratified by smaller spaces of weighted projective hypersurfaces. So you can completely describe this moduli problem as like with these weighted hypersurface pictures. Just gets progressively more and more complicated. Okay. So now let me say a word on the rationality, and I won't get time to talk about the cohomology. So there's a very old conjecture which was worked on a lot by Katzler and Bogomolov, which says that these moduli spaces of degree D hypersurfaces inside Pn are rational. This is a very, very hard question, as it turns out. So the rationality of these spaces, so I haven't stated the conjecture in full, but essentially it's when you take, the claim is that if you take a faithful representation of a group, of a linear algebraic group, and you take its quotient, then this space should be rational. Okay, so it's clearly unirational. You always have the dominant map from your vector space, which you're taking a quotient of. But we don't know, stable rationality is unclear, and rationality is also obviously is unclear, and there are no counterexamples yet. Okay, there is a lot of evidence. So for n equals 1 and all d, this is proven. Okay, for n equals 2 and all d not inside a set of size 15, this is proven. Okay. So it would be fairly big. It's been now about 15 years, I think, since the last one of these got knocked off the list. So we'll be doing well. So I would like to, as part of this old conjecture here, I will throw in my spaces, which I'm interested in. And they fall under the same category. They fall under the same category of the other spaces, so that it's already been conjectured. It's not a new conjecture, is what I'm trying to say. And I mean this specifically because unipotent radicals are solvable. So when you're asking rationality questions, you can often, at least for stable rationality, you can often forget about these things. Okay. Yeah, right. So conjecture is that. Well, I will write down what I think is a genuinely new conjecture, which is that these moduli spaces of, let's say, KR inside P11R, and this is more attainable, are stably rational. Okay, and supporting evidence for this is that, so I'll write down the theorem in two parts. The first part is that, so now let's take the straight case of XD inside Pn. Okay, now this is stably rational under the condition that n plus 1 and d are co-prime. Okay. And this boils down to, so one of two things. Either you can express this quotient as the base space for a C star bundle over an SL action, okay? Or one can prove that Simon and I were talking about, you can show that if n and d are co-prime, this implies that CL n+1, sorry, n+1 here, mod mu d, which is kind of a global stabilizer for these actions, for the representation, is special in the sense of Serre. And so on the locus where you have a generically, on the locus where you have truly trivial stabilizers, where you have a principal bundle, you get a trivialization in the Zariski topology, from which it follows. And now the second part of this theorem, so now these spaces which I was talking about, these RKs, I won't write the full thing, this is stably rational if the GCD of more numbers, so we have n, we have, let me get this exactly right, n 2r, 3r, up to kr is 1. Okay? So this is a lot easier to be fulfilled, right? As you see. So we need in particular all of these to be co-prime, okay, which is more easily attained as for this one here. And then I will finish because I imagine my time is up. The last thing that I wanted to say, which I won't have time, is that also analogously for the hypersurfaces in projective space case, we can essentially revamp computations done by Francis in the 80s and by Tomasi more recently on the cohomology of these spaces. And so finally, is that the D large. So the tagline is the D large, the cohomology of M X D inside D 1 R. I should be consistent. I apologize. Stabilizes to that of BG. Okay. So over Q, we get these moduli spaces. For I less than some constant. Okay. Yeah, I would have liked to have proved it, but next time. Thank you for your attention. Yeah. Yeah. A co-prime. Yeah, essentially this, and you take. Yeah. If you take, exactly, degree D times D prime, then essentially the same thing falls out. So the GIT picture reduces to that of the locus on which you branched off. And this comes from, I mean, again, so it's a little bit more delicate because, so one thing I didn't mention because I didn't write the theorem in full. So this stuff, Josh Jackson and I are working on generalizing this this picture to arbitrary hypersurfaces in Wade's projective space with Cartier degree, but you can't use non-reductive GIT. So it's you have to do it in stages. So you do the first unipotent quotient and then the second unipotent quotient, and that means the weight picture is a little bit more delicate. But the same thing happens. So you will end up like stability in this case if and only if you have non-reductive GIT stability of this thing, if and only if you have non-reductive GIT stability of this thing. And the unipotent stability conditions will ensure that you are only considering surfaces or hypersurfaces which do make sense as double covers, right? So I mean, in this case, you would have you'd have y squared minus a degree 6 in x1, x2, x3. And yeah, your unipotent stability conditions ensure that this never vanishes, basically. You always have a well-defined double covering. And this generalizes to to the case 1's d prime co-prime degree d times d. Yeah.
CKN.
This CKN. So it basically depends. It's It's a lattice point of the polytope count essentially. So you have to you look at your torus. You look at torus weights and you consider semi-stability for torus weights. Okay, for the maximal torus. So I mean, let's pretend we're talking about straight hypersurfaces now. This constant is computed explicitly. Yeah, I mean, I have to. In what I have to write it and think of it as some volume of some polytope or some Earhart polynomial. But Frances, because she's just dealing, I mean, you can really explicitly compute these things. And it is, so a half times this constant of d and n is of the order as d gets bigger to, I think, n times d over n plus 1 divided by n factorial. I think there's something here. But if you're familiar with kind of Earhart polynomials and lattice point counting theory, then these kind of numbers look familiar to the n. Yeah. And essentially the same thing holds. I mean, it's just what's the condition of being unstable? It's missing this. Yeah, I can explain it to you in a little bit more detail later. But essentially, it's what's going on here is that the codimension of the unstable locus is just getting bigger and bigger and bigger and bigger. Right. And that's. So the unstable locus is getting the codimension is getting much, much bigger, right? And so your Tom Gison sequence tells you that this, so again, I should put a star here. And so when this is, yeah, I mean, here, as I've written it, here, this is really Frances's, or generalizing Frances's kind of version for stable hypersurfaces. Tomasi and Vakil and Wood, they get. So here you consider smooth things, and this is again the same thing here. But here I is just d plus 1 over 2, because I mean in this case you're removing upstairs at least you're removing a whole divisor. So you're removing this entire codimension one thing, and you need completely different techniques. But it does mean that you get more for your money in a way. D go, but so you fix n and you let d go to infinity. Yeah, that's a good bit. I mean, the idea, right? So if you think about just hypersurfaces in Pn, the Newton polytopes can kind of contain each other. You see the kind of cubic equations are sat inside your, at least if you imagine it via SLN torus, the maximal torus and SLN, they're sat inside each other like this. And so your unstable locus, which you're taking a sweep of, gets it contributes less and less and less to the cohomology. But yeah, the point is you can write down explicitly what this is. You can put bounds on the. I mean, it's just about putting. I don't think they're optimal, but you can put bounds on the codimension of the unstable locus.
So
Okay. I mean, I'll run you through the proof afterwards. I mean, you can see how it falls out. This is canonical, but it's not like this. I mean, you're actually in the hypersurface case, you're quotienting out by SLN, right? But I mean, BGLN is secretly BS1 tensor. I mean, the cohomology of this guy is BS1 tensor BSLN. But BS1 coincides with the cohomology of projective space for reasonable degree. This is how this guy appears. So it's not a contractibility of the